Hi, folks. So I'm just going to quickly go through what I already went through earlier. And that is that last time we talked about Boyle's law, which is the pressure being proportional to making the same mistake, 1 over the volume. Okay. So the pressure is a constant times 1 over volume. So this is how we end up with, of course, this is at constant temperature, that the product, well, P is equal to a constant times 1 over V, or P times V is constant, or P1 V1 is P2 V2. Feel free to fast forward to wherever it was that you were able to see me up until. Okay, so Boyle's law, that's that. Then we have Charles's law, which is the proportionality of volume to temperature. Okay, so this is an inverse proportion. This is actually a proportion over here. So that means a volume, and this, of course, is at constant pressure. Volume is a constant times the temperature. So the ratio of the volume to the temperature is constant, which means that V1 over T1 is V2 over T2. And of course, this is, like I said, at constant pressure, and this is at constant temperature. But what if both change? Okay, and so we end up with, instead of just P times V is a constant, or V over T is a constant, we have P times V over T altogether is a constant, which leads to P1 V1 over T1 equals P2 V2 over T2. And this is what we call a combined gas law. Okay, the video that I made on this subject has a lot more on it, but the basic idea is that if you know any 5 of these things, you can calculate the 6th. So, so the example I'd like to go through is the same example that's on the video, and that's here. Suppose you have 10 liters of an ideal gas at 35 degrees and 3 atmospheres, and the pressure is reduced to 1 atmosphere and the temperature is reduced to 0. Now that looks like a large temperature change, but it's really not, because if we convert these numbers into kelvins, we have to add 273.15, but that doesn't matter because we have no decimal places on the 35, so we're not going to bother with them anyway. So we have another technical difficulty here. So let's see if I can solve this one. Hold on. Okay, so when we add these together, we get 298 Kelvin. Actually, 308. Sorry, I don't know how to add. Okay, and for 0 degrees, that's just 0 plus 273, that's 273 Kelvin. So basically our temperature is going from 308, that's T1, to T2, which is 273. The pressure is going from P1, which is 3 atmospheres, to P2. So what's happening here is the pressure reduces by a factor of 3. What would that do to the volume? How would the volume change if you did that? Well, since pressure goes down by a factor of 3, the volume would go up by a factor of 3. So that would triple the volume. So we would expect it to go like from 10 to 30 liters because of that. But we also have a temperature change. But that temperature change is not all that dramatic, right? It's from 308 to 273. This is not that dramatic in the real unit you have to use, which is Kelvin. This is maybe a decrease of about 10%. right? Because 30 degrees would be about 10%, and that's about what the drop is, a little more than that. So the temperature dropping a little bit would lead to the volume drops a little. So instead of having 30 liters, when we do this problem, you'll see it comes out to 26.6 liters. And the way I found that out was I used P1 V1 over T1 equals P2 V2 over T2. And one way to do it is to cross multiply P1 V1 T2 equals P2 V2 T1. And since I'm solving for V2, I'll divide by P2 T1. Okay, so that these all here will cancel. And so that V2 equals, and I always write the pressures up and down from each other. You can even consider them as separate factors. It doesn't affect the math. T2 over T1 and V1. And the reason I write it like that is you could see that this is a factor. P1, this is going to be 3 over 1. So that's a factor of 3. T2 is 273, over 308. And that's a factor that's something like 0.89 or something like that. 273 over 308. 89.886, that's what it is. So instead of multiplying by 3 and getting 30, it's a little less than that. And so when you put all these numbers in, this times 10, and you multiply, the kelvins will cancel here, of course, atmospheres will cancel, and you'll be left with liters. And it comes out to, like I said, 26.6 liters. So when you do combined gas law problems, it's good to do a little bit in your head. If the pressure goes down, the volume's going to go up. If the temperature goes up, the volume's going to go up. If the temperature goes down, the volume's going to go down. So temperature and volume are proportional, but pressure and volume are inversely proportional. You should keep that in mind. Okay, there's one more gas law that I haven't talked about yet, and that is Avogadro's law, which deals with how volume is related to moles. So it deals with volume and moles. And this is the old balloon experiment. You know, you blow up a balloon, you put a little bit of your exhaled air in there, and you get a small volume. And then you continue to add more exhaled air. And lo and behold, you get a bigger balloon, okay? So it's actually very intuitive that the volume will be proportional to the number of moles, the amount of the gas that's inside the balloon. So we call that N in this unit. So moles is N. Okay, so volume is proportional to the number of moles of gas. That is if the pressure and temperature are constant. Okay, so that's what I call Avogadro's law, part 1, this proportionality. But there's another part, which I think is almost more interesting, really, because this is kind of, you know, intuitive, really. Part 2 says that equal volumes of two different gases at the same temperature and pressure have the same number of moles, okay? Equal volumes of two different gases have the same number of moles. So why would that be? Well, I have to ask the question, what determines the volume of a gas? And the volume of the gas is not really determined by the identity of those tiny little gas particles. You know, you have these tiny, tiny gas molecules. You know, and actually those dots are way bigger than what a gas molecule is. And what it really is a space in between that matters. And that space is very much affected by pressure and temperature, but not by identity of the gas. That's only going to affect how heavy that little particle is, you know, or anyway, or how big it is, like hydrogen versus ammonia or something like that. But the important thing is that it's really the empty space that matters. And that depends on P and T and not on the gas's identity. So when does identity start to matter? Because it does matter eventually. So it matters at low temperatures and high pressures. These are places where we will get liquefaction. And what happens and why you get liquefaction is you start to get attractions. And the details of the structure of each of those gas molecules is going to determine whether the interactions are strong or weak or whatever they are. And we'll learn about that in the next unit. But identity does not matter right here. So that's a good thing to keep in mind. And we'll get back to that in one of the problems that I'll get to in a minute. So the volume is proportional to the moles at constant pressure and temperature, which means that the ratio V over N is constant, which means V1 over N1 is V2 over N2. And so you can use this very much like those other gas laws when you know, say, an initial and a final volume, and you know the initial moles, but you don't know how many moles at the end. That would be a case where, you know, some gas were added or taken away from a container. So what happens next is that we put these laws together. We have V being proportional to N. We have V being, well, we had pressure being proportional to 1 over V, but that's the same thing as written this way. And we have volume being proportional to temperature, and we have different conditions here. This is for constant pressure and temperature. This is at constant temperature, and this is at constant pressure. But if we put them all together, so volume is proportional to N, it's proportional to T, and it's inversely proportional to P. And then I say, okay, that means that volume is a constant times NT over P, and the constant we call the gas constant for obvious reasons, and it's R. We give it the symbol R, and it's 0.08206 liter atmospheres per mole Kelvin. Those are the units, and the units are kind of important because, hold on a minute. The units are important because it leads to how, you know, you have to put the problem in certain units. You have to put the variables in units that go along with the units for the gas constant. So here, I'm going to put down here. Okay. That was a pretty bad job, but oh well. Anyway, that's what it is. Okay, so we have V is a constant times, oh, sorry, that constant is R. V is R N T over P, or if we write it all together, we can write it as PV equals nRT. And this is the way the ideal gas law is affectionately known. In fact, I call it IGL most of the time. Okay. All right. So when we use this word ideal, so an ideal gas obeys the ideal gas law. And for most sort of normal conditions, in other words, temperatures not too low, the pressure not too high. Actually, the pressure can be pretty high. I would say less than between 50 and 100 atmospheres will still be ideal for most gases. Then gases will be ideal under these conditions. And we don't really study non-ideal gases in this class, so you don't have to worry too much about that. So let's go and just launch into a problem. So what volume will 6.75 moles of carbon dioxide occupy under 420 torr pressure And I put a decimal point here to indicate I really would like you to use 3 sig figs in your answer. So this is a pretty straightforward application of the ideal gas law. This is the moles, so this is N. This is going to be the pressure, but I have to convert. This is, you have to convert torr, which is the same as millimeters of mercury, into atmospheres. Okay, and I'll tell you the conversion factor. It's 760 torr is 1 atmospheres, and this does not affect the sig figs. This is considered exact. So whatever sig figs you have here, that's what you're going to have here. And you have 3, 1, 2, 3 sig figs is 0 counts because there's a decimal point in the number, and this is 0.553 atmospheres, and that's what we're going to use in the equation. And we also have to convert the temperature into Kelvin. We always have to do that with every gas problem. But this is nice because it's pretty easy. We're going to add 273. We're not going to worry about the 0.15 because there's no decimal places there. So we get 373 Kelvin. So we have PV equals nRT. And what is it we're trying to find? The volume. So V is nRT over P. So it's 6.75 moles, 0.08206 liter atmospheres per mole Kelvin times 373 Kelvin over 0.553 atmospheres pressure. And you could see how nicely the units will cancel. Okay, atmospheres goes, moles goes, kelvins goes, and you're left with liters. Okay, and that's good because it's a volume unit. See, 374 liters is the answer to that simple ideal gas law problem. All right, another problem here. Let's see. A sample of nitrogen is held at 25 degrees C, in a 60 liter container. The pressure is 710 millimeters of mercury. It's on the next line. How many grams of N2 are in the container? Okay, so here's a case where the ideal gas law alone is not going to be able to solve the problem because there is no mass in the ideal gas law. All right. So what are we going to do here? Well, we know the temperature, we know the volume, we even know the pressure, although they're not in the right units yet. We'll have to convert them. So what we can do is we can get the moles, that's N, and then we can convert from moles to grams because we know how to do that because we did that last semester. So let's see, 25 degrees C plus 273 Kelvin is 298. That happens to be one that I have memorized. 730, let's call it torr. It's just easier to write. And we'll just convert that, is 0.960 atmospheres. So we got the temperature. Oh, the volume. The volume is 60 liters. That's the right unit, so we don't have to do anything with that. So we have PV equals nRT, and we are solving for the moles. N equals PV over RT. Now, I have to tell you that many students make a mistake, and they'll tell me that N is RT over PV, but you won't do that, right? Good. So, make sure you divide both sides by RT before you get to get the moles. So N would be, let's see, P V over 0.08206 liter atmospheres per mole Kelvin times 298 Kelvin. I did like a little mistake here on the sig figs because this said 25.0. So that signals that I really have to use the decimal places because I have to keep one decimal place in this answer. So you get 298.15, which is actually 298.2. So that's how I caught my mistake, because I looked at what I had written. Okay, so the reason I had to do that in this case was because I had a decimal place in the temperature. So that's really the right way to do that. Yeah. All right, so doing the math, this comes out to 2.35 moles. Okay, so 60 liters. This pressure is pretty much close to atmospheric pressure. The temperature is about room temperature. So if you have a little more than 2 moles of gas, it's going to be 60 liters. That's good. Gases take up a lot of space. Those are standard conditions, almost standard. So what about the mass? So to do that, you have to know what gas it was, right? And it says it was nitrogen. So it was N2 gas. So that has a molar mass of 28 grams per mole. So we'll take our 2.35 moles and convert it. Then we get 65.9 grams. So sometimes you have to know something already, combine 2 different things. The ideal gas law doesn't give you what you want, but you can work with it and get to where you have to go. Okay, and that's why I had to convert, from grams to moles. So the next one is, okay, this next one says, what is the volume of 1 mole of N2 gas at STP? STP is standard temperature and pressure. And the standard pressure we take to be 1 atmosphere, and the standard temperature 273 Kelvin, actually 273.15, but that's okay. So what it's asking is, what is the volume of 1 mole at STP? So volume is nRT over P, right? Because PV is nRT. So this is 1.08206, 273 over 1. And once again, you see all the units cancel. And you end up with liters. And it's a number that I've had memorized since high school. It's 22.4 liters. And why would I memorize that number? I'll give you a clue. It says, what is the volume of CO2 under the same conditions? So it asks about nitrogen, but then it says, what is the volume of CO2 under the same conditions? That's like a trick question, right? Because what's the answer here? Well, from Avogadro's law, right? If you have 2 different gases at the same temperature and pressure, you will have the same volume. So 22.4 liters is for 1 mole of N2, or 1 mole of CO2, or 1 mole of any gas. And that's why it's a good number to keep in your head, because it's for any gas. It's not just a number I'm memorizing for nitrogen under particular conditions. So anyway, I'm just a geek. That's why I really memorized it, because I do that sort of thing. Okay, I mean, you could see there's no information that I used in this problem anywhere that had anything to do with the identity of nitrogen, because it's simply not needed. For ideal gases, all behave the same. So I just wanted to say that activity 2 has several problems. 7 and 8 we did last time. I'm posting the solutions today. These are not problems that you hand in. If you're handing in a problem, I will let you know. And I can't accept all problems from everyone in the class every time. That's just not going to happen. So, sometimes we will do the problems. If we haven't done them and they're not assigned, you should still do them. They're good practice. So what can I say about the rest of the problems in activity 2? Number 9 is a combined gas law. problem, and so is number 10. But number 10 actually is part of graded assignment 1, or GA1. So at least once a unit, probably once a unit, maybe twice a unit, I will give you a graded assignment. Yeah, probably there's only 7 units. I'll probably go for once or twice a unit. And I actually grade these. I give them back. Actually, I'm going to do it all on Blackboard. So you'll have to submit on Blackboard. So you're going to have to look for the folder for graded assignments. And it's not up there yet, but it will be up there before it's due. This is only one of the 2 problems that's on there. The other one is problem 22, which is in a later activity. So anyway, that's a good problem for you to do. And what I ask you to do is not just to solve it, but to explain it. So I don't want you to explain this by saying the equation does this and this and this. I want you to tell me intuitively, why is it that you get the answer that you get in this problem? These graded assignments are about 10% of the grade if you look at the syllabus. And I do drop 1 or 2, so you don't have to get them all perfectly. Let's see. I ask that whenever you submit a file, I would like you to put your last name as at the beginning of the file name, and then the assignment. So I would put Cooley GA1 as the file name. That way, if I have to download your file, I won't have to rename it. I'll know who it belongs to. Most of the time, I'm going to try not to download files, but to grade them on Blackboard, which I hope you'll have patience with me, because it's a little bit of a learning curve there, and I've never done that before. So I'm grading some lab stuff right now, and it's kind of a little bit of a challenge. So bear with me. Okay, well, the ideal gas law leads to a very nice method. I should say it leads to an equation. I call it a method for finding the molar mass of a gas, which we didn't cover, and it's in lab tomorrow. So I'm a little bit annoyed with that, but because I'm covering it now. I was supposed to cover it in class today. But anyway, this is going to be part of this week's lab. And the way that works is that you have the ideal gas law, but if you rearrange it just a little bit, well, actually not, if you realize, okay, so molar mass is not in this equation. So how am I going to put molar mass in this equation? And by the way, I usually use this symbol, the script M, for molar mass, although it's a capital italicized M in the lab handout, because I didn't want to go crazy with fonts and stuff. So there's no molar mass in here, but there's moles, okay? And moles, that's the mass divided by the molar mass. We use that relationship all the time. So N, which is moles, is M over that script molar mass. So what I can do is I can take PV, and instead of writing N, I'll write M over capital M, okay, RT. And so what this basically is PV is little m for the mass, RT, over the molar mass. And then I can just flip this around using a little bit of algebra. The molar mass becomes equal to MRT over PV, which is really kind of cool, because what it means is if you know the mass of a gas, the mass of a gas sample, and you know the temperature, the pressure of the sample, and the volume of the sample, you can calculate the molar mass. Okay, and like I said, we're going to do that in lab, or we're going to look at a video of it. And another thing you can do is if you think about this equation, m is little m RT over PV. But what if I write it like this? I switch the order of the V and the P. And then you look at this. What is this? What is m over V? Mass over volume. That's the density. So that's actually D for density. So what I have is that the molar mass, I'm going to go straight to this one, is D RT over P, where D is the density. So that the density is PM over RT. Or sometimes I write it as PM equals DRT. And I remember teaching this when I had a toddler, a little boy running around getting dirty all day long. And I would say, boy, in the afternoon, PM, the kid's really gotten pretty dirty. So PM, that's how I used to memorize it. PM equals dirt. But you don't have to memorize it. Anyway, so what you can see here, though, is from this equation, D equals PM over RT. You could see that the density is proportional to the molar mass. Well, that makes sense, because if you have one of those samples, like a volume, and you have these tiny gas molecules, now we're talking about the mass of this divided by the volume. And those tiny dots each weigh more because the molar mass is bigger, then the density is going to be greater. So the density is proportional to the molar mass, but you'll also notice it is inversely proportional to the temperature. So as the temperature goes up, what happens to the volume? Volume goes up, but it's the same mass in that volume. So the density is lower, goes down. So density is really very different for a gas than it is for a liquid and a solid, because liquids and solids have fixed volumes. You really can't change those volumes without drastically changing the conditions. But for a gas, the density could be, under one pressure, it'll be one thing, under one temperature, it'll be one thing. Anything that affects the temperature is going to affect the density. So density is not a constant for a gas. It depends on conditions. Okay. Oh yeah, I wanted to talk a little bit about balloons, right? When you have a helium balloon, right? The helium balloon is going up and up and up, right? Here's the ground. If you had a carbon dioxide filled balloon, then the balloon would hug the ground. No, why is that? Well, air is what they are all, present in, right? So we have CO2 in here. CO2 has a molar mass of about 44. Let's call it 44.0. Then we'll be ready for tomorrow's lab. Air, on the other hand, well, actually, we're going to do a problem about the molar mass of air, but it's got kind of an in-between density, whereas helium is 4 grams per mole. Okay, so this is less dense than air. So it rises. This is more dense than air. So it falls. Okay, and we'll figure out the density of air very soon. Okay, so let's see, problem 14 says, what is the density of CO2 at 20 degrees C and 755 torr? Notice it has to give you conditions because the density varies with those things. So first of all, we need to know the molar mass of CO2. 2 oxygens, 32, 16, and 16, and 12 for carbon, 12.01. So 44.0 is right. Then we have to, of course, convert our torr to atmospheres. This is almost 1 atmosphere, 0.993. And 20 degrees C is 2 293 Kelvin. So we have the density is PM over RT. Let's see how the units work out. 0.993 atmospheres, 44.0 grams per mole. How's this going to work out? 0.08206 liter atmospheres per mole Kelvin. Okay, I don't have to put that in parentheses. Put the whole thing in. And then the temperature, 293 Kelvin. So, all right, start the canceling. Kelvins goes. All right, this is 1 over mole in the numerator and 1 over mole in the denominator. So they cancel. Atmospheres goes. And look, you end up with grams and liters. Grams per liter is the unit that you'll get for the density. And it comes out to 1.82 grams per liter. That's the density of CO2. And so now back to the thing I was telling you we were going to get to, which was about the density of air. And here, well, actually, it was the molar mass of air. So the density of air is given in this problem, grams per liter. And then this problem says, okay, air is mostly one gas. I think most of us know what it is. Which of the following gases is the major component of air? Okay, so how am I going to do this problem? Well, I'm going to use my PM is dirt equation. Okay, and what I'm solving for is the molar mass. Because I'm going to use this problem to find the molar mass. And then I'm going to compare the molar mass that I get to the molar masses of these. Okay, so that's how I'm going to do the problem. So D is 1.295 grams per liter, and R, I'm going to run out of room. When you have a tablet, that doesn't really matter. And T is, does it get, oh, STP, standard temperature and pressure, that's 273 Kelvin. So this is 273, and the pressure is 1 atmosphere. And so when I do this math, it comes out to 29. So then when I look at these molecules here, O2, H2, CO2, N2, CO2 we already know has 44 grams per mole. O2 has 2 oxygens, 32. Get this over here. H2 is 2, and N2 is 28. So you can see very clearly that this is the closest. All right. Okay. So when we were going to have class, I was going to actually have you do this in a breakout group because this is good preparation for lab this week. But unfortunately, that didn't work out. So remember, I said that we have this very nice relation between the molar mass, the temperature and pressure and volume of a sample. So if we know M, T, P, and V, we can figure out the molar mass. So here is an experiment that was done. And there's a glass bulb that contains a gas, a type of freon. This is not the same freon that we're going to use in the lab tomorrow. It's a different one. There's many, many freons. This one's called Freon 114. And this is what the empty bulb weighs. So we can find the mass of the freon by taking that difference, which comes out to 1.423 grams of freon when you subtract one from the other. Okay, that's what you get. All right. We also have the volume, 193, but we're going to need to convert that into liters, which is dividing by 1,000. And then we have 757 milliliter, torr, which we'll have to convert, which comes out to 0.996. 21 degrees C is 294 Kelvin. Okay. So if we put this all together, it's 1.423 grams times 0.08206 liter atmospheres per mole Kelvin times 294 over 0.996 times 0.193 liters. Liters cancels, atmospheres, kelvins, and you end up with grams over moles, which is perfect because that's what the molar mass unit should be. And it comes out to 179. So tomorrow we're going to do a cool thing in the lab if I get to play those videos and if it actually works, where we'll actually take a pan of water and we will have a very long, 500 milliliter graduated cylinder, which will fill with water, and I will invert it. Won't invert it that close to the bottom like that. So basically, this is all filled with water. Okay. And then I'm going to take a little canister of carbon dioxide, whatever it is, many different gases we're going to use. And I'm going to have a piece of tubing, and I'm going to dispense the gas through the tubing and into that pan. And when I do that, what's going to happen is that the gas is going to go way up. It's going to go bubble, bubble. It's going to bubble in here, right? And so it's going to start filling from the top down. You're going to see a space, and this water level will eventually come down to the level of the pan. Actually, we adjust the position of this so that the level inside and outside is the same. And that way we know the pressure inside is equal to the pressure outside. And that's how we find the pressure actually. So when we do this in lab tomorrow, you'll see, blank space here, but it'll be, of course, it'll be air. It'll be the gas that was dispensed from the gas tank. So that's kind of the way it's going to look. And then we measure the volume of this cylinder, or the part that the gas is in. And then we have to measure the pressure and the temperature as well. Well, anyway, just to finish this problem, there's another little portion of it that says, what is the density of the Freon 114? Actually, density, there's two different ways we can do this, the easy way and the hard way. The easy way is that we know that density is always mass over volume, and we know the mass, right? That's the difference in the masses of the canisters. And the volume is the 1.193 liters. So this comes out to 7.37 grams per liter. And you can see it's much denser than the CO2, I believe, from the previous example. And that's because it's got a lot of heavy atoms, these freons of chlorines and fluorines and things like that are much heavier than what's in, well, what gas was that? I don't want to make that mistake. Might have been nitrogen. Yeah, no, CO2. It's a larger, heavier molecule. But of course, we could have also gotten this from our PM equals DRT by solving for D. But it's a lot harder and to get the same answer because now we know that it's 179 grams per mole. Times 294. Kelvin. Let's see. And, you know, I was going to try to cover a little more stuff in class today, but it didn't work out. So that's done. That's a wrap. I hope that you have a chance to watch this before lab tomorrow if you're in the lab. And I'll be continuing on Wednesday. Sorry about the way things worked out. I have to tell you, I read everybody's chats and how nice they were, and it almost made me cry. So thanks a lot, you guys. Okay. I bought a new computer. I already had it in the house and I hooked it up, and that's what I'm doing this on. But I have no idea if it's going to work tomorrow. So I think we'll turn the router off for 10 minutes and turn it back on again before class. I don't know. Anyway, have a good night or day whenever you're watching this. And I will stop the recording.